We are going through the topic of spot speed studies, and yesterday we have looked at the statistics we can calculate for the spot speed data. We call them descriptive statistics, and they are of two types. We have statistics for central tendency and statistics for dispersion. Central tendency meaning the values which tell you about the normal values of the data, the normal range of the data, which is mean, median, mode, and pace. Okay, and then we have statistics of dispersion, which tell you about the variation in the data, and they are standard deviation, percentage of drivers in the pace range, and the 85th and the 15th percentile. Okay, and then we looked at the concept of normal distribution, that research has found that the speed data or any data which is taken from real world, it should follow a symmetric distribution, the one which you see in the slide there, which has one peak in the middle, and then the data goes down on both sides. Okay, so this symmetric distribution is called as a normal distribution, and this is how we represent it with the letter n, and then we put two numbers in the bracket to show the mean and variance of the data. Okay, and then we have a specific type of normal distribution which we call as standard normal distribution. Okay, so again it's a symmetric distribution, normal distribution, but it has a mean of 0 and a variance of 1. The advantage of a standard normal is it has a table, which you will see today. Okay, so it has a table. You want any percentile, anything related to the standard normal, we can use the table directly. You don't have to do the calculations. But our problem is that the speed data cannot be standard normal because it cannot have a mean speed of 0. So we have a method to convert our data to the standard normal. Standard normal represented with z. Okay. So you have the data minus mean upon standard deviation. It converts the x value into the z value, and after the conversion you can use the values from the z distribution without any problem. And then we looked at the concept of the confidence interval, the mean which we get, the standard deviation which we get from our data, that is for our sample. Okay, and we want to have an idea about the entire population from this sample. Okay, so we will not take the simple mean, we will take we will use a theorem which is called as the central limit theorem, and it is applicable to normal distribution. Central limit theorem applies to normal distribution. That's why having a normal distribution is important. So central limit theorem says that if you take the mean and then do plus minus 1.96 e. Okay, what is e? This value. Okay, this is e. So from mean, if you do plus minus 1.96 e, then you will get the 95% of the range of the mean for the entire population. Okay, the entire population has a mean or 95% of the mean in this range. Okay, and instead of 1.96 e, if you do 3 times e, then your the population you will cover is 99.7%. Okay, so this is according to the central limit theorem. Okay, and these are the values from our data. Okay, I asked you to calculate the confidence interval for our data. Somebody has done it? Yes, anyone? Yeah. Give me 1 second. Tell me the E value first. Okay. Yes.
48.82. 47.58. $47.25. 49.25.
Okay, So the mean of the data, we have 95% chance that it will be in the above range, and we have 99.7% chance that it will be in the range below. Okay, we are not talking about the mean of a sample, we are talking about the mean of the entire population. Okay, I wrote CI here. What is this CI? Yes? Confidence interval. Okay, and what do we call as a confidence level? What is the confidence level? We have a confidence interval. The range is confidence interval. And what is the confidence level? Yes. The percentage. Okay. So this is a range of mean data when my confidence level is 95%. And this is a range of mean data when my confidence level is 99.7%. Got it? So the percentage for which we are calculating the interval is confidence level. And the range itself is called as confidence interval. Okay? Okay? Sure? Okay. So it can come in the quiz, right? It can come in the quiz, no problem. So if it comes in the quiz, only because of her. Any questions? Normally we use 95% confidence interval. Okay, normally in most of the cases we use 95% confidence interval. Okay, because 99.7% will be too accurate or too much in detail and so on. Okay, so here we don't have any problem, we are just putting the numbers in the equations and calculating it. But when you are doing real experiments or real data collection, then this can make a lot of difference. Okay, so we keep ourselves to 95%, which is reasonable, more than reasonable. You are covering 95% data, obviously. 5% is a very small error you are having. Okay, now if you look at this equation which we are using to calculate the confidence interval, we have the mean. So we are looking for the mean, right? The center of the data. Okay, this is the mean. And in this mean, or from this mean, I'm allowing myself to go this much forward and this much backward, right? Okay, so this is the value I want, and this is the error I'm allowing myself. That in this value, I can afford this much error. I can accept this much error, this entire thing with a plus minus. Okay, so this entire thing is called as a tolerance or acceptable error or allowable error. Okay, so this plus minus thing can be called as tolerance or allowable error or acceptable error. Okay, with the entire plus minus with the E and 1.96 and so on. Okay, so if you are working at 95% confidence level, then you are allowing this much tolerance. If you are working at 99.7% confidence, then you are allowing this much tolerance. Clear? Clear? Okay. Now in this equation, I know E equals to S upon root of N. What was S? Standard deviation. What is N? Total number of values. Okay. So I can replace capital E with S upon root of N. So what do I have? E equals to 1.96 S upon root of N, or E equals to 3 times S upon root of N, right? Depending upon the confidence level. Okay. So I can now shift this equation to calculate N instead of E. Okay. So if you use a 95% level, then N equals to that value on the top. Okay. So it's coming from here. Okay. The actual equation was E equals to this whole thing. Okay. So you replace it with N. So that is the equation for N. And if you are using this equation, then E equals to this. Okay. So in terms of N, it will be this equation. Clear? Okay. So E was my allowable error. E is 1.96 s upon root of n. So n equals to one of these things. Clear? Clear? So these are the equations which you use to calculate the number of samples. Okay. One of you are asking me how many samples we need. We will calculate the number of samples from these equations. Okay. And these equations have different confidence levels, right? Which one I said is more common? 95%. So you will use the equation for 95%. Okay. I already mentioned you have to do a spot speed study for the second part of the project. How many samples there should be in that study? You calculate from the first equation. Okay. Now what are the things I need? 3.84 is constant. We need the standard deviation, right? You already collected a trial data in the first trial, in the first part, right? Use that data to calculate standard deviation. Use that data, the first part data of speed to calculate standard deviation. Then use that value over here. Clear? Okay. E is given in the guidelines. The value of E is given in the guidelines, the project guidelines. Okay. So use that value and S from the last sample and calculate number of samples required. Clear? Okay. Using the first equation. And this is how it is done in the field as well. You want to do a study. You want to calculate the number of samples required, you look for some previous data. Okay, you look for some previous data so that you can calculate how many samples you need. Clear? And what is E? E is, as I said, for the project I have given you, but E is the error you are allowing, the tolerance you are allowing yourself in the observations. Clear? So you fix it according to the standards. Okay? Any question? Okay, so we have this question which says how many speeds must be collected to find out the true mean speed of the distribution within plus minus 1 miles per hour with 95% confidence, and how the results will change if the tolerance is changed to plus minus 0.5 and the confidence level is changed to 99.7%. Okay, so we are using one of these equations. Okay, one of the equations which I showed you earlier. So okay, so what are the things I need? I need S and E, right? What is given from them? E. Okay, the thing with the plus minus is E. This is how we started the derivation, right? So tolerance is plus minus 1 and then it will change to plus minus 0.5. Okay, the confidence level will be 1. You have to use this one and the other one as well, 95% as well as 99.7%. Okay, what other value I need? Huh? The standard deviation. Okay, have they given me standard deviation? Okay, so what did I say? From where do we get standard deviation? Previous data. Did they give us any previous data? No, right? So we have to assume something. According to them, if you are in this situation, then you can assume 5 miles per hour. 5 miles per hour, according to them, is a reasonable assumption. 5 miles per hour is a reasonable assumption. So if you don't have any other value, no other way to calculate it, you can assume standard deviation to be 5 miles per hour. Okay, so now we have 95% confidence and we have 99.7% confidence. We have error of 1 mile per hour and we have error of 0.5 miles per hour. Okay, so we have to calculate the values for these different combinations. Okay, tell me. Uh-huh.
96.
96. Which one?
99.7.
Which one? This one? And this one? Okay, so now you can see when the confidence level increases, values increase. Okay, because now you are trying to cover a bigger part of the population, so you should collect more data. 95%, smaller part of the population, 99.7% comparatively bigger, so you should collect more data. And what happens when you decrease the error, the tolerance? When you decrease the tolerance values, we need more data. The values increase, right? Because less error means more accuracy. Want to be more accurate? Collect more data. Okay? You want to be more accurate about your grade? Keep on taking the course. Okay? 3-4 attempts. Right? Clear? Any questions? Another thing which we do with the speed data is before and after studies. Okay, I call them earlier observance studies or follow-up studies. Okay, they mean same thing. Before and after observance or follow-up studies, they mean the same thing. You want to make some change on the road, and that change is supposed to affect the speed. So you will do a spot speed study before the change, and you will do the spot speed study after the change. Okay. From these two studies, we are trying to answer two questions. By doing before and after study, we are trying to answer two questions. The first question is, did our change had an impact on the speed or not? Maybe you were hoping to get some impact, but in the end, the speed remains the same or almost the same. So this is the first question. Did we have an impact or not? And the second question is, how much is the impact? If there is an impact, obviously. If there is no impact, then the second question is gone. If there is no impact, right? It's the same. So there is no level of impact, right? So the first question is there an impact? If yes, then how much is it? What level of the impact we have got? Okay, so impact could be, okay, there is an impact, the speed reduced, but how much? To what value it has reduced? Okay, this is the second question. Clear? Clear? When you do before and after studies, you have to keep in mind two things. The first thing is that the sample size should be at least 30. The sample size should be at least, okay, but how do we calculate the sample size? We have formulas, right? Okay. So what do I do with the value from here? I have an equation to calculate number of samples, right? And they are saying it should be 30.
Fixed. Fixed.
And then do what?
If it is more than 30, it's better.
Yeah. Okay. You will trust the equation until the answer is 30 or more. If the equation gives you less than 30, you will take how much? 30. Clear? Okay. Same thing for your term logics. Same thing for your term logics. Yes, you will use the equation, the first equation with the standard deviation you have, with the error which is given, but in the end you got a value 25. Then don't take 25. You take how many? 30. Clear? Okay. Now, going back, and obviously both of them should be following the same distribution. Which distribution? Normal distribution. Okay. Now, to answer the question that do we have a significant effect of our change on the speed? Okay. So, for example, the before speed was 80. The after one is 70. What do you see? Is this a significant effect or not? but you thought about it, right? Huh? Everybody thinks it's significant?
Yes.
Hmm? Okay. What about if it is 75 and 80?
There is a measure whether it is significant or not.
Yeah. Okay. Because now you started doing this, right? So then you would do this. Okay. So we have a mathematical way to ascertain that we have a significant change or not. Okay. We don't leave it to the opinion, especially US. Okay. So we cannot leave it to, okay, this guy is saying this is significant, this guy is saying not significant. What do we do? You will have a war in the meeting room. Okay. So to avoid that, we have this method, the mathematical approach, which will exactly tell us whether it is significant or not. Okay. To use this method, we have to calculate two things: Sy and Z. Okay. Sy. Consider Sy as, I'm not giving you a book definition. Okay. Just for the sake of understanding. Consider Sy as the combined standard deviation of before and after sample. So we have taken a sample before change and we have taken a sample after change. If you combine their standard deviation, that is Sy. Okay, just for the sake of explanation. Sorry? Before and after both. You combine both data, this gives you a combined standard deviation. So how do we calculate Sy using this equation? Okay, what do we have here? S1 meaning standard deviation of the before sample. N1 number of samples in the before sample. S2 standard deviation in the after sample. N2 number of samples in the after sample. Clear? Clear? From here then you go to the Z value. Okay, now you will calculate Z value. So you use Sy, which you already have. Okay, you need X1 bar and X2 bar. What was X bar? The mean, right? So X1 bar means mean of which sample? The before. Okay, and that one? The clear? Clear? Okay. What was Z?
The normal distribution.
Which normal? Standard normal distribution. And we said Z has a table, right? That's why we are using it, because then our work will become easier. So this is the Z table. Okay. The values inside the table are cumulative frequencies or cumulative probabilities. Okay. So each Z value in the table has a cumulative probability or cumulative frequency. Okay. The values inside the table are cumulative probabilities. Clear? Okay. Now you may have seen this table in statistics. So how to read it? You are doing this. You are the only one. How do we read it? Then let's say your Z value is 2.00. How do we read this table? Anybody remembers?
2.2.
Yeah.
The first row.
The first column. The first column 2.0 and 0.00 from the top. Okay. So your cumulative probability is what? 0.97 something. Clear? Clear? Okay. What is the rule? The rule is if the cumulative probability, okay, not the Z values, the cumulative probability is 0.95 or more, that means our change has a significant effect on this speed. Okay. Otherwise, it does not have a significant effect. Clear? Okay. If the Z value has a cumulative probability of 0.95 or more, so the table will tell you the probability. Okay. You calculate the Z value first, then you come to the table, find out the cumulative probability. If the value of cumulative probability is 0.95 or more, that means the change on the road has a significant effect on the speed. Otherwise, no effect. Clear? Clear? Okay. Let's keep in mind the common mistake is people do this on the Z value itself. No. Take the Z value. Now you don't know anything yet. Come to the table, find out the probability of Z, then apply 0.95. Then see if it is 0.95 or more. Okay? Got it? Okay? If the Z value is 1.00, then 1.0 here, 0.00 on the top. So how much is the probability? 0.84. So the change is significant or not? No, right? It's not. But if you are just looking at the z value, you will say it is, and that will be wrong. Okay, so we are not looking at the z value, we are looking at the probability of the z. Clear? Okay. Okay. Consider the following results before and after study, and they are checking the effectiveness of a new speed limit. So they put a new speed limit and they are hoping that the drivers will follow it for no reason. Okay, so God knows who are these drivers. Okay, so they see the speed limit, they start reducing their speed. Not at all like you guys. So they have the before data and the after data. For each data set, they have mean, standard deviation, and number of samples. Okay, so first of all, we will try to calculate the SY and the Z value. Okay, tell me. SY is how much? 0 how much? 0? 0, 5. 0, 5. Okay, and the Z value? Any problem till now? Clear, right? Okay. So now, what's the next step? The table. 2.19, so you will look at 2.1 from here and 0.09 from the top. Okay, so this is this value. Okay, it's 0.98. Okay, so what do you say? The change is significant or not? It is? It is significant, right? Yes. Okay, so now we know the new speed limit has a significant change. Okay, now what was the next question? The first question was, do we have a significant effect or not? The next question is, how much? Okay, now here they have told us how much they actually want it to be. Okay, so they want it to be 60. They want the effect to be up to 60. Okay, do we have 60? First of all, where am I looking at? The before or after? After, right? You want to make it 60 after. Okay, did we achieve 60 after? No, right? From this you will say no, right? Okay, but the problem is this is 60 for a sample. Okay, so I cannot say confidently that whether I have achieved 60 or not. Okay, to have more confidence, what do? We calculate confidence interval. To have more confidence in our values, then we calculate confidence interval. Okay, so for confidence interval, we have to calculate the E value s upon root of n and then the confidence interval. How much is my confidence level here? 95%. Okay, we usually play with the 95% confidence level. Okay, tell me the E value first. And then okay. So even if I try to find out the range of mean for 95% of the data, I still couldn't find 60. Okay, so now I can say yes, we have achieved a change, but that change is not up to 60. Okay, and I'm how much sure about it? 95% sure about it. Clear? Okay, this is why we calculate the confidence interval, so we can be more confident about our answer. If somebody gives the answer that 60 is not achieved on the basis of the sample, it is acceptable but with low confidence. What he is saying is true, it's not wrong. If you look at the sample of 60 cars, the value is not 60, it is 63, right? So what he is saying is not false, but it's not reliable, it's not that accurate. So when you calculate confidence interval, now you become, or your answer becomes more accurate, more reliable. Clear? Everybody? Okay. Now we say that our data follows normal distribution, right? The speed data follows normal distribution. How did we say this? Based on what? The shape of the graph, right? We said the shape of the graph is symmetric. Okay. What shape?
Bell shape.
Bell shape. Okay. So it's a bell shaped graph, right? Okay. So now again the problem comes that who is making the graph? Huh? Okay, we are making the graph, right? Okay, and we have some engineers among us, we have some artists among us, right? So you can make any shape of the graph you want. Okay, now you have to submit the drawings for your roads as well, for your segments. And I know some of you will make the curvature of the roads without knowing the radius. Okay, some of you do this, right? It looks beautiful. Huh? But it's not true, right?
Which drawings?
Huh?
Which drawings exactly?
We need to draw the segment, the road segment you have. You need to draw it. Okay? And some of you, since the road is going like this, let me make it like this. What is the radius? We don't know. Where is it going? We don't know. Where you are going? You don't know. Okay, clear? Okay, so again the problem comes, we cannot leave it to the shape of the curve. Now, you can leave it if you joined all the points. There were 20 points, we joined all of them and it made a curve, fine. But we didn't do this. We didn't join all the points. We made the best fit curve, if you remember. The actual curve, the actual point, we didn't join all of them. We just said, okay, the curve should be close to the points and it should be best fit. That's it. Okay, so now it's more doubtful. So again, just like what we did in the previous case, we applied the z value. Here we will apply another value which is called as the chi-square. Okay, so chi-square value was a test which will tell us if the data has normal distribution or not. Okay, if the data has normal distribution or not. So how do we calculate the chi-square value? You can see the equation on the board here. So don't call it x square, because if in the exam you ask me for the equation of x square, I will not give you. Okay, it's chi-square. Okay, just for the sake of the course. So what do we need here? We need n and f. What was n? No, this n, the one which you see in the equation. We are using n in the equation, right? We use n in the mean equation as well, standard equation as well. What was n?
Total.
Total was capital N. This one is
Times of the frequencies.
in each group. This is the actual frequency in each group. The actual frequency in each group. The actual number of observations in each group. What is F? Theoretical frequency in each group. So we have the actual and we have the theoretical. N is actual, F is theoretical. Now to calculate the chi-square value, I have to go back to the data. Okay, this is the data which we already have. Okay, what did we do this with this data? First of all, I start with the highest speed group which has a value. I start with the highest speed group which has a value. Okay, so that means that at the bottom I will have the lowest group. Okay, so if your highest speed group has 0 values, you will not put it in. Okay, so you can see I am starting with a group which has a value. The value for the first group is how much? 2. How much is the value for the first group? 2. So if there was a 0 group, a group with 0 value, I have removed it. We don't use it in the chi-square. Same thing for the lower group. You will end at the lowest group which has a value. So if your lowest group has a value of 0, you remove that one and take the next lowest one. Okay, so this one has a value of 5. Okay, now with these groups, for the top group, the highest one, you will take the upper value and put infinity there. Take the upper value, put infinity. And then take the lowest value, the lower value of the lowest group, and replace it with minus infinity. Okay? So, highest on the top, lowest at the bottom, highest and lowest groups with 0, remove, highest value infinity, lowest value minus infinity. And then with them you write the values which you have observed for each group in the field. Got it? Okay. So this group was actually 34 to 32, the last one. Actually. Okay. And its frequency was 5. So I remove the 32 with minus infinity and keep the frequency. No changes in the frequency. Clear? And values. Okay. Next thing, for each upper value, for each upper limit, you will calculate its z value. How to calculate the z value? This is the equation. You take the value, x will be your value, minus mu. Mu is the mean of the data upon standard deviation. Mean, standard deviation. Okay? Clear? So for example, you took this value, 34. So x will be 34. Mu is the mean of the data. Now this is the data which we have used yesterday. So we already know its mean, we already know its standard deviation. If you don't know, you have to calculate it. Clear? Okay? So the mean of this data was 48.2, the standard deviation was 6.1. Okay? So what do you do? 34 minus the mean 48.2 upon standard deviation 6.1. Clear? For the next group, it will be 36 minus mean or standard deviation. Clear? Okay. Any questions? Now you look at the first value. What is the first z value? Infinity. Why it is infinity? Because the first upper value is infinity. Will it change? Will it change? No. Because we change it to infinity. We are putting the infinity. Okay. So the first one is infinity. After we calculate the z value, we go to the z table. We have a z table, right? Okay. So you take each value, each of the z value, go to the table and find out its cumulative probability. Okay. Now you look at the first z value is infinity, right? So its cumulative probability is how much? 1.
Why is it 1?
Maximum z value, right? So maximum cumulative probability is how much? 1. Can the probability be more than 1? No. So if it is infinity, the highest probability I can give is 1. Clear? Okay. Now you see for each z value, you go to the table and find out. You see some negative values there as well, right? You can see some negative values. If you are using Excel, Excel can give you probability for negative z as well. If you have a statistics book, then you will find a bigger table with 2 pages, and you will find 1 page for the positive value, 1 page for the negative values. Okay, those people are very nice. They want everybody to get an A. We don't. Okay, like we want C's and D's. They are good for us. So we have this one. In the exam, you just have this table. Do you see any negative z value here? No. You just put negative in the table. I just put negative with your answer, and your grade will be negative. Okay, everybody will be asking me, why did you give him -2? Okay, so don't do this. Nobody will ask you. That's the funny thing. All of them are asking you, okay, what do you do with the negative value? So for example, you have negative 0.03. You have negative 0.03. You don't have negative 0.03. Minus 0.03 is not there, but you have 0.03, right? Okay, so what do? Take the value for 0.03. So 0.0 on the top and 0.03 this column, right? So the value is 0.51. 20. Okay. So what do? We drop our calculators so that we can leave the exam, right? Okay. So if you want it for minus 0.03, then it will be 1 minus okay. So if you want it for minus 0.03, take the probability of 0.03 from the table, and then you do 1 minus the probability. Okay. Again, a common mistake is people do 1 minus that value. Okay, we are doing 1 minus probability of z value. Clear? Okay. Another rule we said about infinity, right? That for infinity the probability is how much? 1, because this is the maximum, right? Is that true for any value which is more than the value of z in the table? Any value. Do you see a value of 4 here? No, right? So even the value of 4 will have a probability of 1, because the last probability here is 0.999 something. After 0.999 you will have 1. Will it go more than 1? No. Okay. So any value which is more than the value of z of the table, we will assign a probability of 1. And if there is a negative value, take the probability of positive, then 1 minus the probability of positive. Clear? Clear? Any questions? You are having a question? No. Okay, so up till now we have filled the first 6 columns of the chi-square calculations. Okay, the first 2 columns were speed groups. We just arrange them, put infinities and so on. The next column, values which you have from the field. The next column, z value for each upper limit, and the next one is probabilities which you are getting from the table. If the probability is more than the table, the z value is more than the table, probability is 1. Z value is negative, then take the value of positive, 1 minus z. Clear? Any questions? Okay, so we'll continue with the same table tomorrow, inshallah.